In this chapter, we are starting to talk about two different kinds of reasoning. The first kind that we're talking about today is inductive reasoning. And you've used inductive reasoning before. Anytime you saw a pattern and you made an educated guess about what was coming up next, you were using inductive reasoning. I want to, however, bring your attention to some new vocabulary. Up until now, anytime that you have put your phone away, anytime that you have thought of making an educated guess, what was the term that you associated with that, making an educated guess? You called that? No?
Hypothesis.
You called it a hypothesis. In this class, however, a hypothesis is actually something different. Okay, so in this class, when we are making an educated guess, we are making a conjecture. Okay? So in problem 1, you see that we are making a conjecture about what the next two terms of this sequence are. For part A of problem 1, please don't tell me what the next two terms are. Can someone please tell me what's happening in part A of problem 1? What is happening in this sequence? Don't tell me what the next two terms are. Tell me what's happening. Sarah? It's getting doubled. 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. So now, very easily, everybody could tell me what the next term in the sequence is.
64.
It's 64, thank you. And then when I double that, that's 128. For part B, actually drawing that out would be really time-consuming and annoying, so I'm not going to actually draw it out. But I would hope that you would realize that it's going to be a bunch of squares. So what is happening to my number of squares? What is happening to my number of squares? It's not doubling. Look at it again. Well, all of the squares, yes, are getting smaller, but here in my first one, I have 1 square. Here in my second term, I have how many little squares? I have,
You're adding more times 4.
I'm multiplying by 4. Yes, so again, I'm not going to draw the diagram because that would be really time-consuming and tedious, but I'd hope that you would realize that in this third term, I have 16 squares. So in the, gentlemen, in the next term of the sequence, I would have 64 squares. And then in the diagram after that, I would have 256 squares. Problem 2 is, actually problems 2 and 3 are really popular kinds of questions to see on SATs or ACT, especially because probably those are timed tests. And on a question like problem 2, if a student doesn't have an actual strategy, what might a student be tempted to do? Write it out, and they'd sit there and go 1, 2, 3, 1, 2, 3, 1, 2, 3 until they get to the 25th term. And that would be not terribly awful in a problem like this, but of course on the SAT or ACT, they might ask you what is the 101st term, and how time-consuming and annoying would that be? So, we want to develop a strategy. Does anyone have a strategy?
Wait, so are you saying how many? I don't understand what you're asking.
What I'm asking, or what the problem is asking, is what is the 25th term in this sequence? Notice that it's a repeating sequence. 1, 2, 3, 1, 2, 3, 1, 2, 3. What it's asking is what is the 25th term? What I'm asking is, rather than write this out, let's come up with a strategy. Can you think of a strategy? Taylor?
I have one question. Is like
Okay, question.
Like the number 1 term, and 2, another 1 term.
This is the first term, second term, third term, fourth term, fifth term, sixth term. Okay. So, here's probably the easiest strategy I can give you. First of all, do you remember back when you were in this little desk in elementary school, before you ever did division with the decimal point, you did division with a remainder. Please tell me they're still teaching remainder in elementary school.
I remember that.
Oh, okay.
Yeah, it was a little
Okay.
odd.
Right. Okay. So, yes, sir.
I know the answer.
Okay, hold that thought. So, the process, the strategy that I want you to employ is to first figure out how many terms we go through before we repeat. So how many terms are in this repeating sequence?
3.
There's 3 repeating terms. So, as I mentioned, you're going to sit in this elementary school desk and you're going to divide thinking remainder. Do not think decimal. Okay, so we're going to take 25 and divide it by 3. Now, I'm not so much interested in the number that's in front of what you might get in the decimal. Here's my question, first of all. Let's remember how to divide with a remainder. How many 3's go into 24? I'm 25. 8. And then, more importantly, what's my remainder?
1.
Remainder 1. That remainder tells us what part of the repeating sequence is your answer. So, since my remainder is 1, I look at the first term in my sequence, which was 1, and there's my answer.
I thought I'd have to go back to reminders. That was phase in my life I was done with.
Okay, before I go any further, because I had a couple of students earlier asking me, I don't get how you found the remainder. Should I clarify the whole remainder bit? Yes, okay. So, you understood that when I asked how many 3's go into 25, it was 8. 8 times 3 is 24, and when I subtract those, that number is my remainder. Just kind of refreshing your memory a little bit. Okay? Before I move on to problem 3, which is big time, should I do one more example like this one before we move on to something a little bit more complicated? Another example like problem 2?
Sure.
Okay. So, suppose my pattern is A, B, C, D, E. A, B, C, D, E, ... Okay, 2 questions. Let's say, what is the 52nd term and what is the 100th term? First thing you identify is how many terms in my repeating sequence. How many terms?
5.
There's 5 of them. So I take the term that I'm trying to find and I divide it by the number of terms in my sequence. So we're doing 5 divided into 52. And if the numbers start to get to a point where you just can't resist and you have to pull the calculator out, that's fine. Just understand that point, nobody cares about that. Okay? What's important to you is the remainder. So if you really, really had to type this into your calculator because you just didn't know what to do without it, you would get 10 point, the 10 is what matters to us. So the 10 is what I use to find my remainder. Remember, 10 times 5 is 50, and when I subtract,
B.
I end up with a remainder of 2, which means that, yes, B is my 52nd term. Yes, ma'am. Whoa. Hold that thought. I'm going to end up answering that question. Okay, look at that last example. There it is. Gentlemen, we all right back there?
All the time.
All right. So, this next question, what is the 100th term? What is the 100th term? Some of you already realize there is no remainder. Now, think about this. Hold on. Let's come back to the sequence and realize that every 5th term was the last term of the sequence. So let me say that again. This is term 5. it's E. This is term 10, it's E. Notice that when I take either of those numbers and divide it by 5,
So it's E.
I have no remainder. So my 100th term is therefore E. If it's something that you've got to write down in order for it to really sink in, you might want to write down, when there's no remainder, the answer is the last term before it repeats. Does that make sense? Okay, now let's get ready to think deeply. Sometimes you're not even given the pattern. You have to kind of come up with the pattern. So in problem 3, notice they're asking for the sum of the first 40 even integers. Like I said, this would be a question that the SAT or ACT would love to throw at you because it's a timed test. And what's somebody going to be tempted to do? Sit there with their calculator and go 2 plus 4 plus 6, and that's going to suck up all their time. So you want to make sure that you have an idea of how to come up with a strategy. And here's our strategy. When we have something like this, are we all right back there, gentlemen?
Ethan's having a problem.
Okay. What you want to do when you don't have a pattern is identify the first few terms of that sequence. Okay, so I'm going to identify the first, let's say 4 terms of my sequence. So it's talking about the sum of the first 40 even numbers. What's the first even number?
2.
Thank you, 2. So then I know that the sum of the first even numbers is just 2. What are the first 2 even numbers?
2, 4.
2 and 4. So when I add them together, I know that the sum of the first 2 even numbers is 6. And then keep going. I get 2 plus 4 plus 6. I get 12. I get 2 plus 4 plus 6 plus 8. I get 20. Now some of you may be thinking, well, Mrs. Clouse, you said that you were not going to sit here and add and add and add. Well, I'm not certainly going to add all the way to the 40. But I want to develop what the pattern is so that I can kind of come up with a formula. And here's what you want to be thinking of. You do not, let me first start with what you don't want to do. You don't want to be asking yourself, what can I do to 2 to get 6? What can I do to 6 to get 12? What can I do to 12 to get 20? Because that's not going to help you unless you're willing to go all the way up to finding the 39th term. That defeats the purpose of what we're trying to do. You have a thought?
But what if somebody does a different amount of terms?
You'll end up in the same place in the end. Okay, here's what you want to be asking yourself. You want to be asking yourself, what did I do to this number to get my result? What did I do to the term number to get the result? So what did I do to 2 to get 6? What did I do to 3 to get 12? What did I do to 4 to get 20? Take a moment. What you want to be asking yourself is, what can I do to 1 to get 2 that I am also doing to 2?
Well, I don't know, I'm just guessing. Like 1 times 2 is 2, 2 times 3 is 6, 6 times 4 is...
That's exactly it. That's exactly it. Notice what she observed. She observed that for my first sequence, I multiply it by the next number and I get my result. For the second term of the sequence, I multiply it by the next number, I get my result. For the third term of the sequence, I multiply by the next number, I get my result. Same thing. And now, say that again? No. Good question, though. Do I have to do that all the way to 40? No. But here's my question. What am I going to do to 40 to figure out what the
39
sum,
times 40.
40 times who?
39.
No, not 30.
41.
40 times 41.
Good job.
And you get what, 1640?
Can you go back over the step before?
Absolutely. So, let's make sure that I know what step you're talking about. You understood how we identified our even numbers and we added them up according to the description of the pattern. I did the first number, I got 2. I did the first 2, I got 6. Okay. So, what Kristen observed is that in my first term of the sequence, my first term is 1. What's the number that comes right after 1? 2. She multiplied 1 by 2. Oh, look, I get my answer. And I do the same thing for each of those, and I end up with my result. So what she observed.
Wait, so you mean the sequence like when 1 through 40 you did this?
If I were to do 1 through 40, we would notice this same exact sequence, that the sum of the first 40 numbers would end up being, just like Benjamin observed, 40 times 41.
So for like the next one, it would be 5 times 6?
Exactly.
Okay.
Exactly. Okay? So, kind of pitching it to you now, you have your turn for problems 1, 2, and 3 to be working on within your groups individually, however you best work. Let's talk about the answers to the your turn. Oh, because it's frozen. Right, the first your turn, Isa.
Yes.
Oh, was that not your hand?
25 and 20.
25 and 20 are the next 2 terms. Oh, question.
Does that audio thing record the whole class?
Yes.
That's bad.
I think you'll be all right. How about the your turn for 2, Caitlin?
B's.
The third term, it would be B, yes, because there is no remainder. And then finally, the your turn for problem 3, Haley.
900.
It is 900. Before I go any further, I'm reasonably confident you understood how to do the your turn for 1 and 2 on your own without any difficulty. Problem 3, as I said, was the deepest thinking we're doing today. Yes.
Okay, I understand what we do.
Hold on a second. I would love to answer your question, but somebody dropped their manners.
I understand that how we do number 3, like for the your turn, but for that, I don't understand how you got 40 times 41 when it's pretty much the same thing.
But it is different because in the your turn, what you observed is that for my first term, my answer was 1. For my second term, my answer was 4.
Oh, I get it. Never mind, I get it because it was 2 and then
The next number. You see it now?
no, never mind.
Okay. And shh. This one is a little bit harder to see than the odd ones. The evens are a little bit more difficult. And please understand, by no means am I expecting you to memorize that in order to find the sum of the first whatever integers, you take the number and you multiply it by the next number. I'm not expecting you to memorize any of that. What I'm expecting you to be able to apply is this line of thinking, of coming up with the first few terms of the sequence, asking yourself, what am I doing to the number, the term number of the sequence? Like this is term 1, this is term 2, this is term 3, term 4. What am I doing to the number of the term to get the term? Okay, and what was observed is that my first term was the result of taking that number 1 and multiplying it by 2. My second term, the result was that term number times the next.
Okay, so those are supposed to equal that number.
The 2 times 3 equals the 6. The 1 times 2 equals 2. The 3 times 4 equals 12. The 4 times 5 equals 20. Had I gone through and listed and added all 40 of the first even integers, I would have ended up with this. But conveniently, we noticed the pattern, and we were able to come up with that answer without doing all that adding. We just did one simple multiplication.
Okay, so you should do 4, and then, like, for the last one, you do 4, and then whatever times 4 should equal. No?
I don't want you to get hung up on what happened in this sequence. In this particular sequence, I ended up multiplying by the next number. In the your turn sequence, I ended up just being able to square that number.
No, I mean, for, like, number 1, you did 1, what would multiply to get 2, and then, so, like, for 4, you do...
You're asking yourself, what am I doing to 4 to get 20?
Okay.
Okay. The next couple of examples, I think, are, yes, sir.
Your turn thing, what was the answer?
900. 30 times 30.
How is it?
We just went over this.
30 times 30, I thought I had one more.
Hot calling the kettle black.
What?
I know, right?
Okay, so, did you do the sums?
I did 30 times 31.
But that's a completely different sequence. If you did the first 4 terms of odd number sums, you would have had 1, and then 1 plus 3 is 4, and then 1 plus 3 plus 5 is 9, and then 1 plus 3 plus 5 plus 7 is 16. And what was observed is that I take the term of the sequence, I square it, and I get my answer.
Yeah.
Next time, a little less jibber jabber back there, and you might catch what's going on. Then move away from him. I don't have time.
I get it.
Let's move on.
It'll come over now.
Sorry about that. All right, in problem 4, it's a very visual situation where we're making a conjecture based on the way this graph looks. And please understand, your answer doesn't necessarily have to be the exact same answer as my conjecture, but as long as we're both in the same ballpark, we're fine. Okay? So, Isa, you have a conjecture.
No, for from 3.
Oh my god.
If the answer's 100, 170.
No.
It's
900. Okay, those of us that have been paying attention and following along would like to move on. Yes, sir.
I have one more quick question about problem 3.
Yes, sir.
So,
He's listening. He gets to ask the question.
for like the second term, what am I asking?
I don't know. Okay, come to me individually and I'll be happy to help.
Okay.
All right, so in problem 4, what I would hope that you'd realize is that these points are approximating a line. So if it makes your life happier, kind of extend that line. And what might be a good conjecture about how many lift tickets they will sell in February? What might be a good conjecture? Say that again? What would be a good conjecture for how many tickets they will sell in February based on this graph? Sir?
600.
600 would be a perfectly acceptable conjecture. Just for the sake of clarity, can someone give me an example of what would be a really bad conjecture based on the graph? Can someone give me, whoa. Kristen?
700.
700 is kind of out there. If you're guessing 200, that would also be kind of a bad conjecture. Okay, anything in the 500 to 600 range, I would say you're good. Okay, the last bit of vocabulary that I want to address is what is a counterexample. And before I talk about a counterexample, I want to kind of make something clear to you. In order to prove that something is true about numbers, it's a really long and drawn out process. I'll tell you, I didn't learn how to do it until number theory in my junior year of college. It's it's an elaborate process. Whereas disproving something, saying that something is false, very easy. I just need to give one example. For the purposes of clarity, let's lose part B, just because it deals with stuff that we really haven't covered here. It's not common knowledge type stuff. Whereas in part A, the statement, if an animal is green, it is a frog, I would hope that you'd realize, oh, that's not true. So can one person please give me an example stating that that is false? A counter example. Kristen.
For the frog,
Mm-hmm.
do you want something to tell you why? Because leaves are green.
But
That weekend,
But it's not an
right,
animal.
but a leaf isn't an animal.
Oh,
So I want some.
alligators are also green.
Okay, so an alligator is a counterexample, and you don't even have to write a nice, fancy sentence. You just have to give an example for which the statement is false. Because an alligator is green, but it's not a frog, it's a counterexample. In part C, can someone give me a counterexample for the statement, when you multiply a number by 2, the product is divisible by 4?
Oh, wait, so you have to have something that's opposite. Okay.
Something that demonstrates that this is false. A counterexample.
When you multiply 2 times 3.
When you multiply 3 times 2, you get 6, and 6 is not divisible by 4. That would be a perfectly fine counterexample.
What about me?
I don't like B just because it involves stuff that we really haven't gotten deep enough into. Just don't want to even look at it. Okay? So, that's my entire lesson. There is a daily quiz on Socrative. Like I said, you score 100% on it on your tracking chart for your performance tracking sheet. Bubble that first bar if you get 100%. If not, then that's something that you need to improve upon. And I will be working on putting the book up on the screen. 731-855. Okay. All right. I'm glad I stopped the recording. Oh, I thought I